All right, so today we're going to do the testing for differences between means where the standard deviation, population standard deviation is unknown. So, two possibilities. Again, the standard deviations for the population are unknown, the samples are random, the samples are independent, and the populations are normally distributed, or both samples are at least 30. So the first possibility here is if they are not equal, if the population variances are not equal, it's a big, big, ugly looking formula. Okay? So the top is the same as yesterday. We're going to subtract the means minus, what is this going to be? 0, because we're assuming the means are the same. Okay, that's always the assumption. On the bottom, you have the sample standard deviation squared, which is the same thing as the sample variance, divided by the sample size, plus the second sample standard deviation squared, divided by the sample size of the second sample. That's all under a square root. So you got to be careful how to maybe do the top and then do the bottom and then do your division. So it's a little bit less likely you're going to make a mistake with your calculator. Because we're using the t-chart, the degree of freedom, if you have two different sample sizes, you're going to use the smaller one, n minus 1 is the degree of freedom. So your degree of freedom, you're looking at the smaller sample size and take 1 away from it. If the standard deviation, or the population variance or population standard deviation, whichever, are equal, again, it looks real complicated, but the formulas, after you start putting numbers in it, it's not that bad. The top's the same. On the bottom, it's n minus 1, which is kind of the degree of freedom of that sample, times the standard deviation squared, plus n minus 1 of the second sample, times the standard deviation squared, all over sample 1 plus sample 2 minus 2, times the square root of, those square roots should be separate though, and one square root should end. Big formula, okay? The degree of freedom, you add the sample size together minus 2. Here's your guidelines. Identify the claim, state the null and alternative hypothesis, specify the level of significance, determine the degrees of freedom. So again, depending if you have equal population variances or not. So n plus 1, or n1 plus n2 minus 2 if they are not equal. Yeah, there were formulas. If they are equal, it's the top one. If they're not equal, it's the smaller of the sample size minus 1. Then you're going to go to the critical value, find your critical value on the Z table, identify the rejection regions. Then you're going to find your test standardized statistic, which is that big formula that we just talked about. Pick the right one, and then is it in the region or not? Okay? And then interpret the decision in the context of the original claim. Let's go. Here we go. The results of a state mathematics test for random samples of students taught by 2 different teachers are in the same school are shown here. Can you conclude that there is a difference in the mean mathematics test scores for the students of the 2 teachers? Use alpha equaling 0.10. Assume the population is normally distributed and the population variances are not equal. So we're using this formula because the variances are not equal. And we're using this degree of freedom. Okay? Not equal, you pull these. So, first thing we're going to do is state our null. So the claim is there a difference? So the claim is going to be there is a difference. The null is there isn't a difference. And the alternate is there is a difference. Okay? So is this a one-tail or a two-tail test? Two. So we're going to go to our T-chart. And our degree of freedom, which sample size is smaller, 8 or 18? 8. So we're going to go to the T-chart, look at 0.1 for a two-tail test, and you go down to 7. And I get 1.895. So our critical value what'd you say? 8.95. Okay, so put that on the curve. It's plus or minus, because it's two tails. 1.895, negative 1.895. So there's our rejection regions. Anything beyond those? We're very carefully going to fill in this formula that's crazy looking. So using your pencils, write it all out first, then pick your calculator up. I would do it separately just so that's, make sure we're doing okay. So the first sample's mean is 473 minus the second sample's mean. Minus 0, so we don't have to do that part. All over square root of first standard deviation squared over the sample size plus second standard deviation squared over the sample size. So you practice putting that in your calculator. I'm going to give you the answer, but make sure you can get it. If you don't get the right answer, it doesn't work. All right, so it's really just knowing when to use which formula and putting it in. If you were to type that in, the top has got to be put in parentheses. Is everyone able to get it? Still working? Okay, 0.922 falls here. So, are we going to accept? Are we going to reject, or are we going to fail to reject? We are going to fail to reject, because this is in the good region, right? So, fail to reject the null. And then how you would write the next part is you would say, there's not enough evidence to reject the null hypothesis. What does that mean about our claim, guys? We are not going to reject our null. So what does that mean about our claim? We reject the claim. There's not enough evidence to support the claim. Not enough evidence to support the claim. So again, the null is not always the claim. You've got to know if it's the same thing or not. I am not going to reject the null. Our null is basically saying they should be the same. Okay? Make sense? Take your time. All right. We're going to try one more. This one is going to be the bigger formula. You've got a manufacturer claiming that the mean driving cost per mile of its sedans is less than that of its leading competitor. You conduct a study using 30 randomly selected sedans from the manufacturer and 32 of the leading competitor. Your results are shown below. At a significance level of 0.05, can you support the manufacturer's claim? Assume the population variances are equal. So it's a much more complicated formula. Okay. So our degree of freedom is going to be 30 plus 32 minus 2. So our degree of freedom is 60. Sorry, let's stop. What's our claim? Our claim is that his is less than the other guy's. So this is the claim. Our null hypothesis is what? Greater than or equal to. Is this a one-tail test or a two-tail test? One-tail, is it right or left? Left. So our critical value needs to be negative. Okay, so go critical value, get your Z chart out. Our degree of freedom is 60, and we have a left tail of 0.05, 0.05 and 60. I get 1.67 negative, 1.671. That's our critical value. So there's my rejection region. Now find your T score using that formula. And it's big, guys. Big long formula, but you can do the subtracting one in your head, right? So it's not that crazy. So I would do it separately. I would do the top and then the bottom, however you need to do it. It should equal negative 1.93. That's what it should equal. So check your calculators, make sure you can put that all in, however you're going to do it, so you get negative 1.93. Okay, if it's negative 1.93, it's right here. So we are in the rejection zone. So we have enough evidence to reject the null. Therefore, we have enough evidence to support the claim. Okay, so we have enough evidence to support the claim that his company has a smaller mean driving cost. Okay, so try to put your interpretation in respect with words to what they are actually having to test. They'll just say, yeah, we're going to support or reject the claim. Kind of write me a sentence if you would, please. Okay? We good? I'm going to put up the math Excel and you guys can start it.